In a world where cars drive themselves, planes fly themselves, and cars can fly themselves too, there's a crucial building block that powers all of these: controls and dynamics. Controls essentially models the system: a car, a plane, or a robot, and how it interacts with the environment as it moves through it. Simply put, it involves taking all of the inputs from the sensors and outputting what the actuators are supposed to do. But bringing your model to the real world is where things start to get messy. And this is because we start to deal with unmodeled forces like changing friction, wear and tear, changing temperatures, and even things bumping into your system. And so messing this up can be catastrophic. It's hard enough to properly model one system. Now think about the system going through multiple environments, changes to the system, embodiments of these, and variations across all of these domains. This is no longer a trivial problem. This is the Foundry Alley, where we dig a little bit deeper into products and their journeys. I sat down with Ted Lutkus, the founder of Onyx Robotics, to understand the problems in controls and why it's so hard to get your modeling right. Onyx is developing the controls and simulation layer along with the tooling to empower controls engineers. We go through his founding journey from trying to build and commercialize a hardware product, the lessons from that actually led to identifying a crucial gap, and the founding of Onyx. We talk about what companies struggle with when trying to build their own control stack. Finally, we go through system identification and understand the crucial question of how much and where you really need AI in this whole mix. Whatever your background, I'm sure you'll have a lot to take away from this, just as I did. And if you're a developer in this space, you'll probably nod along. Please help me welcome Ted Lutkus.
Before starting Onyx, I was pursuing a PhD in robotics over at Northeastern University. I was always really in love with sort of mechanical systems and where that meets up with controls. And and so when I started my PhD with Toshka Padir over there, I gave him a heads up when I started, which was that I'm in love with these subjects, but I know that I want to start a company someday. Um, and and so I started my PhD, and it actually did not take very long before the sort of urge to start a company and really build in this space sort of took a hold of me. So I dropped out actually, in my first year. Well, first I took a leave of absence, as in good faith one would do, and it was actually to the advice of my advisor, who kind of said like, "Hey, I think that these PhD classes and obligations are, potentially going to be a distraction for you if you're like really in on starting this company. And so, you might want to kind of sneak out the back door here for a little bit and explore." So that sort of set me off on what kind of became like a self-funded PhD and laying the research foundation for what we're doing. Um, maybe notably, I actually started out with a sort of research pursuit that did not become Onyx's core product. Definitely a pivot moment that happened somewhere along the way, before starting this sort of controls and simulation stack that leverages learning-based methods that are really becoming dominant in robotics today, um, and building a product around that stuff so that we can disseminate these methods in robotics, but also more broadly speaking than robotics, in all kinds of industries like automotive and industrial applications and beyond.
What was the problem you're like originally after?
I was kind of obsessed at the time with this idea of a mechanical system that would let us essentially drive an entire robot with one motor, and distribute its mechanical power out to all of the joints.
Mhm.
And maybe notably, hydraulic systems are one way to do this, but instead of valves, I wanted to use a system that would let us actually change the gear ratio of all the joints with pumps. And so instead of using valves, we would use pumps. And this would allow us to really amplify the payload of robotic systems and speed depending on the task at hand. That it presented some really nasty controls and simulation problems. And so the other kind of trick I had up my sleeve at the time was I was watching a lot of the success from, for instance, like Marco Huter's group in ETH Zurich with
Mhm.
training actuator networks on their animal quadruped. And the idea more broadly that you can kind of get around some of the nasty dynamics of a system that you're dealing with by leveraging learning. And, I think it's through the awesome effort of their team and their hard work and kind of building up scar tissue that it seemed like the research community was starting to figure out the right recipes and how to train models for this kind of low level hardware modeling.
Mhm.
And I was convinced that I could potentially use these methods for my, really performant mechanical system and kind of cross this gap of performance and control on a system that was otherwise really nasty to work with. The thing I did naively, though, when I was starting my company was place more value on the sort of novelty of the hardware I was working with.
Mm.
And, so I spent, maybe 2 years working on that hardware and trying to commercialize it. Um, and during that process, I sort of learned two things. One was that no one wanted to buy my hardware. But two, I was talking with all of these hardware companies I was trying to commercialize with and realizing that pretty much no one else outside of the robotics ecosystem was really using or leveraging the same kind of controls and simulation stack that I was seeing in the quadruped community.
Like, what was the constant feedback? Like, how many customers did you have to talk to realize, hey, like actually, there's value in the simulation or in the software side?
Um, so it's over, over a period of time, it just sort of became more and more clear to me that there was a real opportunity to potentially build a pretty transformative product in this space, um, and really build out a tooling layer that would potentially allow us to leverage these learning based methods for kind of system identification and control in ways that would benefit not only robotics but tons of other industries as well. And so I made that pivot
Mhm.
sort of at the end of 2024. And so it's been a little over a year now of building out this tooling layer and getting our first customers on board. And it's been a much more pleasant experience than the hardware pivot before it. But many other founders have similar experiences. One of the challenges I think that founders face, especially like the first time they're like entering into the space, is there's certain kind of like instincts and uh, clarity in like understanding the person you're talking to. Things that you pick up on over time that you don't pick up on early on. And early on, you come in very wide eyed and you have this awesome idea and you think the whole world is going to love it. And so you kind of like might have a conversation where, most of the conversation is like the person basically telling you, like, effectively telling you indirectly that they don't actually care about the thing that you're doing. And then they say one thing that you kind of then pick up on, you're like, oh, this is validation. And so I
Mhm.
think it's actually more to do with a sort of rewiring of your brain. And especially as a robotics founder, I think many of us are fundamentally optimists about technology and where things are going to go. And so it takes a serious kind of rewiring of your brain to like be in tune with is this someone who's just interested in what I'm doing, like, yeah, cool, whatever, or is this like going to solve a really like serious problem for them, and as a startup in a business context that
Mhm.
is associated with dollars. And once you start having that conversations that are more in that latter category, it can become abundantly clear to you that like, oh, this is going to actually solve like a meaningful problem for you and generate some value for your business. And maybe the thing that I did get right early on was being incredibly curious about the questions I was asking.
Yeah.
So the only way I was able to navigate from a hardware domain into, software domain, like two seemingly different worlds, is by asking questions like, you know, well, what matters to you when it comes to performance? Like, what do you care about right now? Like these general questions. And if you came in with the right idea up front, um, someone would answer those questions, those general purpose questions, in a way that validates your idea. But if not, it gives you a blueprint, right? And if you talk to enough people, like in the hundreds, then it'll be pretty clear to you what kind of the common threads are. Um, and then maybe the second piece of that then is, once you find out the thing that actually would be valuable, you also have to answer the question like, do I care about that problem? Um, and one of the things that was nice in my case is that I started out by talking with people building hardware and companies who cared about performance. And it led me to the control side even further. And I love talking with people about controls, and people in controls love talking about controls. So the other piece of it is like, I was pulled in the direction of what we're doing now, but I also kind of came in feeling just excited to help out kinds of people who we talk with, and that was another big piece of it too.
Yeah, awesome. Let's move into Onyx and how
Sure.
all of the learnings kind of fed into this. So yeah, tell me a little bit about, what the product is now. How are your interactions different with the same customers, maybe?
So we're fundamentally building what I think of as a new tooling stack for learning based controls and simulation. Um, Now, what that means is, you know, it's not hard today to train like one neural network, maybe using an existing MATLAB license or following a PyTorch tutorial. I can do that on my data. Uh, but in robotics, a lot of the breakthroughs and the work of these like great labs has been taking the baseline tools and really deeply understanding how to use them well. And so a big part of what we're doing is embedding a lot of the scar tissue of the robotics community in how to train models well for low level dynamics modeling, the low level physics of hardware. Um, we're embedding a lot of that insight into a training pipeline, and into a product that allows a controls engineer from any domain who has deep
Mm.
domain physics expertise to essentially get aim assist in training models that just end up working better than if they had to go build all of that scar tissue on their own. Um, so it's sort of a tooling layer that maybe is also acting as a bit of a like, it's adding this extra sort of layer of AI expertise to a controls engineering team, whether that team is in the robotics domain or in automotive or aerospace. We want to kind of be this agnostic, hardware agnostic product that can take time series data from any of these systems and produce models that predict the dynamics of these systems such that you can accurately simulate them and then build really high fidelity control systems for them.
So is this meant for the hardware companies or more of the software companies that are building out the autonomy and such, or both?
Well, it's important to mention that there's sort of the higher level, let's say, autonomy and planning of a system or decision making that's going on, what to do in the event of a tire blowing out or something like that. And Onyx doesn't really engage with that layer of the stack. All the autonomous driving companies, they want to own those components, and we're interested in this like larger soft white underbelly of hardware systems worldwide. So we're interested in talking with folks that are all over sort of the ecosystem. We can use this tool pretty agnostically across wildly different hardware embodiments. So we fit in at the low level hardware layer.
Say I was a controls engineer, what challenges should I expect to face that you think a learned model would do better at?
Yeah, well, interestingly, like the controls community has kind of, I think, in many ways, always been a half step towards using a learning-based model. We do something called system identification in controls and in simulation all the time. Um, and this is basically, we write down a first principles analytical model, like a mathematical model of my system. So if this is a drone, I write down maybe a simplified drone model that will predict how the drone would fly in space due to the propeller thrusts being applied.
Mm-hmm.
The problem is that the real world is more messy than than that simplified model, even if I know basic parameters like the mass of the drone.
Mm-hmm.
And so in an effort to get my physics models to look more like the real world data we collect, we'll do system identification, which is basically fitting extra parameters in that physics model to the real world data.
Mm-hmm.
But invariably, I'm not I'm gonna sort of do that fitting and then realize that my model is still off by a bit. And this is where in controls engineering, it's sort of the skeletons in like everyone's closet, is that we then start to do things like fit, add in extra polynomial terms and sort of additional combinations of coefficients that like don't necessarily match the first principles physics. And you can think of this as like trying to take a simple model and generalize it to dynamics that it's not really, it's not actually modeling. So, so our belief is actually not to fully go into a learning-based model as a way to ditch all of first principles physics. We're big subscribers to the idea that you should keep all of your first principles mathematical models where they're accurate and where they're useful. But then all of that just added complexity that I can't reach. Either I don't have a good way to write it down by hand, or it's going to be really messy and nasty to maintain. Like, if I'm trying to model weird latencies in
Mm-hmm.
that drone system, and maybe these latencies are going to change each time we have a new build of the drone. Onyx is kind of taking a stance of combine both these worlds where they work really well, but keep a really clean and nice isolation of them. So I
Mm-hmm.
have my simple first principles models, and then do what we do great with deep learning, which is learn all of the residual physics and dynamics
Right.
through the data. And so that paradigm, which is just we're coming in and capturing all of the stuff that's really complex in the data with a learning based model, we do that in a way that's like very seamless and plays really nicely with all of your first principles models. And maybe, the best part is it will remove all of the really tedious manual tuning that I would otherwise have to do and
Yeah.
extra testing I would have to do as a controls engineer.
That's it for this part. In part two, we'll go a little bit deeper into the product, where Ted will show a demo of how to use some of the features, and we'll go into some of the technical details about learning residual physics. We'll also understand using foundation models versus small language models and some of the trade offs associated with those. So I'll see you in the next one. Be sure to follow Ted and Onyx Robotics, and thank you so much for watching.